Hey guys, 4.1 inverse functions. So what I want to do is I want to look at two different functions, and you can graph these on your graphing calculator. You can plug in points. One of them is going to be f of x equals x cubed, and what you'll notice is I labeled a few points on here. I did -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. Okay. The other one that I graphed was g of x is the cubed root of x. Okay. And notice I labeled some points here. -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So once again, you can plug that into your calculator. You can plug in these x values to verify that those are the correct function values. What I want you to notice here is that the x coordinate here is the y coordinate here. Same is true here, even though these are the same, it's harder to see, but the y coordinate here is the x coordinate here. It's like I've switched all my x and y values. That's the first thing you really want to notice. When this is true for all of the x in their domain, we say that f of x and g of x in this case are inverse functions, okay? We can get one from the other by switching the x and y values. So that's one way we can think of inverse functions. But you also want to think in terms of, well, what does the word inverse mean? Well, if you invert something, it's like you undo it. If you invert a glove, something like that. So that's the other thing I want you to keep in mind as we go is inverse functions undo one another. Let's look at another one. What about f of x equals x squared? I've labeled a few points on here, okay? And my question is, well, what would the inverse look like? Well, if we follow the same sort of scheme we did above where we switch the x and y values, I expect to have 4, -2, right? If I switch these values, I expect to have 0, 0, if I switch these, which is the same point, and I expect to have 4, 2 if I switch these values. Now, if I plot these, here's what I'm getting. There's these 3 points. And here's the question is that the inverse function? Well, there's a problem here. This isn't a function. It doesn't pass the vertical line test, okay? Well, what gives? This was, right? So what's the problem here, okay? Well, unless we restrict the domain of x squared specifically to only the positive x values or the negative x values, we're going to get something that isn't a function. So not all functions have inverse functions. Okay, that won't always be true. Okay, so in this case, there is no inverse for x squared. Okay, all right, let's look over here now. Next thing I want to talk about is a one-to-one function. A function is a one-to-one function if, for elements a and b in the domain of f, a not equal to b implies f of a is not equal to f of b. Okay. So what does that mean in layman's terms? That means that each element in the range came from a unique element in the domain. So remember how we used our vertical line test to check if we had a function. This amounts to using a horizontal line test to see if it's one-to-one. So it kind of makes it's a little more exclusive, you could think of it as. So let's look at some examples, okay? In fact, the horizontal line test, I guess it's the first thing we should look at. A function is one-to-one if every horizontal line intersects the graph of the function at most once. Okay, so for example, if we look at this one, first thing I want to do is I want to make sure it's a function, of course, which it is. It passes the vertical line test. Now I use the horizontal line test, and it also passes. So if I pick any y value, it has a unique x value. It's just kind of reversing what we would check for a function, right? So this is a function, and specifically, it is one-to-one. If it's one-to-one, that implies it has an inverse. Okay. Now, if I look at this one, it is a function, right? In fact, we did look at this earlier, but see, it keeps failing the horizontal line test, right? If I pick a specific y, I get multiple x values that map to that y. So this is a function right here, but it is not one-to-one. Okay.